Okay, thank you very much for the kind introduction. And also I would like to thank Adrian and AutoQ for putting us together here in this wonderful place and with many different topics, but all related to the materials and also SNON in this case, or other techniques to visualize the nanoscale. So it's for me it's always every 2 years a way to go, this conference. So I hope you keep doing it. So I will talk today about nano-optics. So some of you are from different communities. Yesterday we saw several talks on twistronics, also on excitons. Here I will show you, well, there were several talks before, like the one from Professor Basov explaining about nano-optics, and also the one from Cheng-Wei Chu. But I will go a little bit on some details on why this is nano-optics, how can we do it, what materials we are using to do this, okay? So these figures that I show you here, these images, they are all SNON images on different materials, actually. These two are on molybdenum trioxide. This you can remember from Cheng-Wei Chu's talk, where he saw that there was canalization, so one regime where using this material you can find that the light propagates in one specific direction. And this is because this light, or this nanolight, in this material is strongly anisotropic. So it propagates very differently upon different in-plane directions. And this gives room for engineering the propagation of light at the nanoscale, okay? And actually, what we do with this layer of MO3 is using another one, twisting them, and getting these kind of regimes. This is what I'm going to show you later in more detail. And this one that I have here is just the latest work we have published this year. And it's another material. It's not molybdenum trioxide. It's lithium vanadium pentoxide. It's the vanadate that is intercalated with lithium atoms. And it also has a permittivity that is strongly anisotropic, and somehow, naturally, this nanolight gets canalized in one direction, only with one layer. Okay, so let me first go to one introduction slide that maybe for many of you is not needed, but I still would like to comment on it. So we cannot do nano-optics with normal light, with propagating light from the far field, because of the diffraction limit. We cannot. We have this limitation of wavelength of light divided by 2, multiplied by the refractive index. So we cannot go to 5 nanometers, 10 nanometers, 50 nanometers wavelengths if we don't use X-rays. But we don't want to use X-rays, right? So one solution is to excite a surface wave, which is a surface polariton. It's just a solution of Maxwell equations. It's an evanescence wave. And because of its character of light, as Dimitri has shown very nicely with the Hopfield model, its dual character of light and matter, it involves some excitation in matter. The dispersion of this wave is to the right to the light line, meaning that for one frequency, its momentum is larger, so its wavelength is much shorter. But it's an evanescence wave. It decays exponentially, so we have to do things fast and small scales, because the energy is lost quite easily. So this was something that was very well known on metals with plasmons, surface plasmons, for decades. But there were problems. There were good things, and you know, applications like SERS and etc. But at the same time, the lifetimes of these waves are very short, 10 femtoseconds. So if you want to do something that requires longer times and so on, you need to find another polariton, for example. And one of them is the phonon polariton. With the same Maxwell equations, you can find that the condition to have a surface wave is that the permittivity of the material is negative. So meaning that it does not allow the incident field to penetrate. It's like a mirror. But by doing so, with a negative permittivity, does not permit the field, it creates a surface wave that reacts to this incident field. So normally, in plasmons, it's the free electrons, right, that react to the electric field, and then they create this movement that screen out the incident field and create this surface wave. But we can have also polar crystals where one of the atoms, normally they are biatomic crystals, where one of the atoms is more electronegative than the other, and therefore the electronic charge is more around one atom, and it creates a natural dipole in the lattice. that can react negatively to this electric field, so it can move this vibration of the lattice, screening out the incident field. The same way. And in physics, it's just that we have a negative permittivity. Okay? But what happens is that this lattice is reacting to this field, trying to screen it out. And by doing so, it creates a surface wave. But in this case, the matter excitation is the phonon. Okay, what happens with phonons is that the scatter, phonon-phonon scattering, it occurs in longer lifetime. So if we excite these surface waves, the lifetimes are in the picosecond range. So we have more room to play around with them. The other characteristic is that they happen when the permittivity is negative, which happens between the TO and LO phonon frequencies. So in the infrared, far infrared. So we don't have, like in plasmons, that you can play with visible light. Here we have to play with infrared light. Infrared, I mean 10 microns or beyond 10 microns. 7 microns to 20 microns wavelength. OK, so we have this to play around. Here I want to say that Fritz, Rainer, and Thomas Taumer, they were pioneering this kind of studies 20 years ago. They were working on, at the time, with silicon carbide, a material that was not so easy to play with. So the new kit on the block appeared, Van der Waals materials, and with them, more flexibility to work with. And some of them, for example, they support plasmons, graphene, or black phosphorus. And some others support phonon polaritons, like boron nitride, topological insulators we saw before, and I will show you that molybdenum trioxide and others. And more others are appearing now. Okay? So, and this is a fantastic sketch from a paper from Dimitri. Yeah, here you have other excitations that can be seen probably in the near future. These are seen, but these two are still there for you to explore. But I want to tell you one thing. So these surface waves are really confined, right? They occur at the nanoscale because the momentum is very high. So it's also very difficult to excite them. You need to match the momentum of the wave to launch it. So normally this was done in plasmonics with auto configuration, Kretschmann configuration, and so on. It's kind of complicated from the experimental point of view. Here, for example, with graphene plasmons, we saw that the confinement was even stronger. So you will need more momentum to launch them as well. And this is when a couple of papers, theoretical papers appear, and they say, OK, if you put a point dipole close to the surface, this point dipole will have enough momentum to launch the waves. And OK, this was immediately trigger our mind said, OK, our SNOM, which is basically, you know, the metal tip, like an AFM tip, but it's metallized, it can have a tiny point dipole source at the tip apex. So if we put our system on top of graphene, maybe we can see these waves. And this is what we have. Why is it so? This tiny here light spot at the tip apex is a concentrated electric field. Sorry. It's a concentrated electric field. And just by Fourier transform in real space this image, you go to the K space, and you can see that something that is really localized in the real space, it has a broad shape in momentum space. So you have enough momentum at the tip apex to launch these waves that are highly confined. This is actually what shows this curve. And the SNOM tip can do this, and Dimitri showed this experiment that it was a very easy experiment, I have to say, experimentally. We just put the system there with the graphene flake, and we saw these fringes. Interferometric fringes in this case. What does it mean? This is what Dimitri explained, that the tip is launching the wave is going to the boundary and comes back to the tip. So the tip is the source and the detector. Therefore, the periodicity between fringes is λ². OK, this is what is called polariton interferometry at the time. But I want to make you aware that instead of using a metal tip, you can also use the SNOM with a silicon tip. Just a dielectric tip that we use it as a scatterer to get the fields that are there excited by other things, and we pick them up and send to the far field, like an experimental green function that is there at the nanoscale, sending everything to the far field, to the detector. This we can do with a silicon tip, and here we have to use a source. And therefore, we fabricated a gold antenna there on graphene, and with this gold antenna, we were launching the graphene plasmons, as the tip was doing before, and then we were using a silicon tip to pick them up and send them to the far field. And actually, doing this, you can see the real propagation of the wave. Otherwise, you are always seeing what is coming back. It's an echo detector. In this way, it's not. It's just taking the photograph of the field that is propagating, focusing or diverging. Okay, so I wanted to call your attention on this, because it's not very widely used, but it's, for looking at the nanoscale, at nano-optics, it's very useful. The only thing is that the scattering cross-section of the silicon tip is much smaller. So typically, you have 1 order of magnitude less signal. Okay? But still, you can see graphene plasmons. OK, so now, after this short, well, I don't know, maybe it's already long introduction, I have to go to this mode 3, where the light, these polaritons, propagate very anisotropically. You can see here, with hyperbolic waves. What does it mean? If you now take here the Fourier transform of this image, you go to the momentum space, and then you get this hyperbola. And then you understand what the hyperbolic propagation is. You have different cases that are available to propagate. OK, this one, this one, this one, this one, this one, this one. But by definition, I want to tell you that the Poynting vector is normal to this curve, which is called the isofrequency curve. So meaning that you have a 1K, available K, but the Poynting vector is pointing in another direction. So energy goes in one direction, and the wavefront is tilted in another. So energy goes in this direction, and sometimes the wavefront is completely tilted. This has strong implications in nano-optics, because refraction, reflection, they all go with momentum conservation. So what we saw is that if you do experiments with this norm, you can see that because of this non-collinearity between K and S, reflection can be negative. So if you want to see yourself in a hyperbolic world, you need to tilt the mirror. So you cannot see it in a normal way. And we also show that you can have anomalous, and the paper from Chen-Wei Chu show that you can have even negative refraction because of this non-collinearity. Very interesting fundamental stuff that you can visualize at the nanoscale. OK, and with this, I go to twist optics. Chen-Wei Chu already showed some of these results, because 4 groups published at the same time, the same thing. We all have the same tool. The materials are there. I have a friend that says that Van der Waals materials democratize material science, because every group in the world can buy very cheap crystal, exfoliate very easily, and make the samples. This is very good. Years ago, yeah, I remember you were talking about the gallium arsenide to this and so on. Only very few groups could work on that, right? And now we can have all with very high mobility to the gases and so on. At the time, it was very difficult. Now you can get it very easily with these materials. And then, well, we can do this experiment. So the bad thing is that we publish all at the same time. Sometimes our wave functions overlap, and sometimes constructively, but other times, many times, destructively. So here I want to introduce a little bit of twistronics, because we are doing twist optics. The famous Pablo in the States do twistronics, also Spanish. So I'm Pablo as well from Spain. So I say, OK, I can do something maybe here. And then I cannot compete with this, but maybe we can also twist layers. And then so instead of doing moire physics, electronic coupling, we took 2 layers of this hyperbolic material in the plane and twist them. OK, can this be twistronics? And then I put here something. Maybe I don't know if it works. Yes. So you have the 2 hyperbolas, and then you can rotate one to the other. By doing so, if you just rotate one overlap on the other, you have a hyperbola. You don't change anything. So you have hyperbolic isofrequency curve. But you can also rotate them and put them, for example, 90 degrees, and then you close the curve, the isofrequency curve. So therefore, you go from an open curve, which is hyperbola, to a closed curve that is a square, something close. So the topology changes of the isofrequency curve. You can call this, you can give a number, a genus number, genus of 0 and genus 1, and then there is a topological transition between them. You need to go from an open curve to a closed curve. And physics is always kind of exotic and nice when there is a topological transition. And therefore, we thought, OK, let's fabricate the samples and see what happens there, OK? This is what we have done. As I told you, we just exfoliate and rotate the samples. We put a 30 degrees angle, and we saw hyperbolic propagation. Nothing really nice. It's just the same propagation, but slightly directional, tilted a little bit. OK, we can manipulate this propagation, but still it's not so nice. If we put a 90 degrees, we have the closed curve, and then we have kind of isotropic propagation. And what happens in the middle? How long do you have? 5 minutes. OK, good. And then, wow, that was really fast. So what happened in the middle? I mean, 54 degrees. And why 54? OK, we tried many, OK? And now I show you here the one that was nice. We saw this. And look, what we have done here was fabricated an antenna here and used the tip just to probe the fields, because we wanted to see the propagation. We don't want it to launch and see the reflection. That's why I did the introduction as well, OK? Therefore, we have this canalization. And this canalization is defined in the isofrequency curve by two parallel lines, two flat curves. Remember, flat bands in twistronics, flat curves in twist optics. And what does it mean that the curves are flat? It means that you have all available Ks. Here I can show you. So we rotate some angle where the asymptotes of the hyperbola, they align in one direction, but they don't align in the other. So you can have destructively, let's say, interference in one of the asymptotes, but constructive in the other. And the final result is two parallel lines. And the good thing about two parallel lines is that you have all Ks available, but the Poynting vector that is normal to the curve is only one direction. So everything propagates in one direction with all Ks. Ks, local density of state. So you have all wavelengths propagating on the same direction. This is good. Then we just measure, we did the line profile, and we saw that there was not a spreading of the geometrical spreading of the wave. It was everything on the same direction, but this is more technical. I will not go now. And here I show you, as Chen Wei Chu showed, it got several prizes, and there were 4 papers, more or less at the same time. We published in Nano Letters, they published in Nature. It was really painful, but well, it's what it is. So now trilayers. We are not very original, you know. We put another layer and we twist. So let's see what happens if we twist. Actually, we can reorient the angles as we wish. We can make, with the same structure, we can put the layers, pick them up, rotate them again, and make another reconfigurable structure. OK, and by doing so, first of all, we calculated numerically what happens with different angles. This is the angle between the first and the second, and this is the angle between the first and the third one. And then you have a lot of possibilities. And you can see that there are many kind of parallel lines at different angles. So we thought, OK, maybe we can have canalization not along one direction, because in bilayers it was defined by the hyperbolas. Maybe we can have canalization in many other directions. Then we thought, OK, maybe we can do analytical. They show these calculations on one single layer of graphene that is in air. You know, this theory guy that said, OK, this is very nice, but it's impossible to realize experimentally. We are experimentalists. We said, OK, let's try to do some model that replicates our experiment. So we have to take into account the layers with thickness and even with air gaps in between. This gets complicated, OK? Look at this. And this is what one of the PhD students were working on. I said, OK, don't worry. We can maybe numerically solve this analytical equation and so on, but we can get insights on that. So finally, we got, for example, one sector here, and we confront here numerical calculations with these analytical calculations. And then you can see the red ones are analytically calculated curves that they overlap really on the numerically ones. So we have a tool that allows us maybe to predict canalization and other regimes. OK. So, but there are multiple photonic magic angles, OK, angles of the layers where propagation is in one direction. And then we fabricated the samples with this dry transfer stuff. We did these 3 layers. We changed the angle of the top layer, for example, reconfigurable. We measured with a Snow tip, one antenna there to launch, everything the same. And then we saw that canalization can go in different directions. Okay? You can get canalization in the direction that you want if you change the angles as you wish. So, and then you have these parallel lines where you have this canalization, high density of states, and so on. So there are indeed. So now we use an analytical theory, and we can calculate that actually you can have whatever angle you want. Some of them, they have a larger spreading angle. So you have a canalization, but it's not so canalized. But some others are really narrow. And this is really different to what you have with two layers. Okay? So 3 layers, they give you more room to play around with this canalization of light. It's not only that. In frequency, it's robust. So the isofrequency curve are 2 parallel lines along, within some spectral range. And this is what we wanted to check, and we tried at different frequencies, and all of them were canalized along one specific direction. So you have a broadband. Well, broadband is much to say when you are here in 30 wave numbers range, but for phonon polarities, it's quite OK. OK, so and this is something that, PowerPoint physics that you were saying, you need to sell it. Maybe we can do some canalization where you can rotate the layers and then try to bring light wherever you want, doing this kind of stuff. And maybe, and this was a collaboration with Dimitri, maybe doing some rotation of the layers in situ so you can manipulate all the twist angles and so on. Well, it works, but it's not so efficient at the moment. I think, do we have 1 minute, or is just 1 minute? OK, so just the last one is this layer of lithium vanadium pentoxide, where you can have loss-induced canalization. Now we have 2 layers, 3 layers. But I tell you, if you do a very simple numerical experiment, where you have a material that is isotropic in the plane, and then you put here losses in one direction, but also a very small real part of the permittivity, these 2 conditions, first condition, second condition, you can get canalized light in one direction. Basically, the other one is too lossy, and the wavelength is very large. So you can switch it off there, the propagation. OK, so can we get this in reality? We found this material, lithium vanadium pentoxide, that exactly at some frequency range, these 2 conditions are met. So we measure it with the fantastic tool, SNOM tool. We could see the propagation, and here you can see how it goes elliptical, and it goes here canalized. We only see 2 fringes, but doesn't mean that it's very lossy in that direction. The group velocity is very, very small in this case. So the wave is propagating very slowly, but the lifetime is 2 picoseconds. Okay? It's really long for being polaritons. So maybe if you want to send information, long distance is not the right choice, but for cavities, it's probably a good choice. Okay? With this, I want to thank all the people working on this in the group. And I put here some names of the people directly involved in these works. And some of them are around, and they have posters if you want to see. With this, I also want to thank the collaborators, of course, Alexei doing all the theory, Raina, and also people from Copenhagen, and also the money is important to say thank you, and thank you for attention.